Minerals are the building blocks of the Earth, but did you know that minerals themselves are commonly made of shared building blocks? We can visualize the crystal structures of these minerals using a series of 3D printed building blocks called TotBlocks. In this video, we'll look at the Brucite group, which is the only group of non-silicate modular minerals in this series. Brucite is named after Dr. Archibald Bruce, the mineralogist who discovered it. The Brucite group consists of metal hydroxides with various cations like magnesium, iron, and calcium bonded to hydroxide groups. Brucite is the magnesium hydroxide member of this group. Gibbsite, an aluminum hydroxide, has a related structure, and we'll look at the differences between these minerals later on in this video. Brucite and gibbsite are ore minerals for magnesium and aluminum, which are used in lightweight alloys and household items. This is the crystal structure of the Brucite group, which consists of O-layer modules. Now we'll take it apart. To construct the Brucite structure, connect double chain with O+ modules widthwise to illustrate the sheeted nature of the structure. Missing sites between the horizontally connected modules can be filled using single octahedron pieces. To vertically stack the sheets, pegs are inserted into the slots of the O layer. As an added note, there are two sides of these pegs. There is a triangle on one side and a hexagon on the other side. So the triangle will go into the bottom layer, like so. And the hexagons will go into the top layer, over here, 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 and here. The Brucite group consists of infinite sheets of O modules, and in the case of Brucite, each of these octahedral M sites are filled with magnesium cations. Ferrous iron and calcium can also substitute in these sites, producing amaconite and portlandite, for example. Of the three elements that I just mentioned, all of them have a charge of +2. Gibbsite is also a hydroxide, but the element in gibbsite is aluminum, which has a charge of +3. How is this possible? Well, imagine that this honeycomb of M sites is separated into groups of 3 M sites. If all 3 M sites are occupied by magnesium, then we get a charge of +2 times 3, which equals +6. But a charge of +6 could also be rearranged into 2 sites, each having a charge of +3 plus a vacancy. That is, a site with nothing in it, which looks like this. We can extend this structure to get an idea of how it would look for an infinite sheet. To put a name to these two structures, we go back to the sites that we started with. The configuration on the left has 3 octahedra, whereas the configuration on the right has 2 octahedra. Thus, the configuration on the left is referred to as trioctahedral, whereas the one on the right is dioctahedral. Now we can see that brucite is trioctahedral, whereas gibbsite is dioctahedral. But the beauty of modularity is that we can apply this principle to other minerals. The trioctahedral and dioctahedral configurations apply to all minerals that have infinite sheets of O modules. In the 1-to-1 phyllosilicates, serpentine is trioctahedral, whereas kaolinite is dioctahedral. The 2-to-1 phyllosilicates also have trioctahedral and dioctahedral forms. Talc is the trioctahedral counterpart to the dioctahedral perophyllite, and in the mica group, the biotite series, which consists of annite and phlogopite, is the trioctahedral component to the dioctahedral muscovite. Finally, the chlorite group is a bit more complex because it actually contains 2 different O modules, so several configurations are possible. In clinochlor and chamosite, the most common chlorite group minerals, both of the O modules are trioctahedral. On the other hand, in donbasite, both of the O modules are dioctahedral. We can also infer the habit that brucite crystals will develop by going back to the sheeted nature of the O modules. These O modules can be extended infinitely, and this scales up to a platy habit in visible crystals. Similar to the 2-to-1 phyllosilicates, brucite also has a basal cleavage located between the O modules. In this video, we've explored the brucite group and taken a closer look at the configurations of the O modules, leading to a distinction between the trioctahedral and dioctahedral modules. We then extended this further to other layered minerals that have O modules in their structures. Finally, we've seen how the sheeted nature of these modules leads to a platy habit and basal cleavage in this group.